Well, good afternoon, everyone, and welcome to today's joint EOL ACOM seminar. On behalf of EOL and ACOM, I'm pleased to introduce Dr. Michael Lawler. After obtaining a bachelor's in Earth and Planetary Science from University of California, Berkeley, Dr. Lawler earned his master's and doctorate in Earth System Science from the University of California, Irvine, on the cycling of reactive halogen compounds in marine air. In 2012, he started a postdoc, technically at the University of Eastern Finland, but physically based in Enkar in ACD, now ACOM. There he started working on new particle formation processes, and since then his focus has been on aerosol composition and processes. Dr. Lawler returned to UC Irvine as a project scientist, working mostly on marine and Arctic aerosol formation for several years before taking up his current position with CIRES at CU Boulder, working embedded in the Chemical Sciences Laboratory at NOAA. His current work involves aircraft-based single particle mass spectrometry to look at aerosol composition. He still works on some marine aerosol questions, but his large focus of late is on the UTLS region. On that note, please join me in welcoming Dr. Lawler for his seminar titled Meteoric-Sulfuric Particles Formed in the Winter Polar Vortex, Their Size, Composition, and Fate.
Thanks very much, Sarah. Thanks for the kind introduction and for inviting me. Thanks for reaching out. It's nice to be back. It's been, I used to work here some years ago in the chemical division. But now as Sarah said, I'm in CIRES at CU Boulder, and yes, embedded at NOAA, CSL. I'm not a NOAA employee. It's good to keep those things clear these days. I'm going to talk to you about some work we did a couple years ago in February, March of 2023. So we were up in Alaska at Eielson Air Force Base, and we were really trying to get at processes affecting stratospheric aerosol around the polar vortex. And I'll acknowledge my co-authors on this slide who contributed data and analysis and feedback on this work. Okay, so just to give an overview of the talks, I'll motivate, why do we care about stratospheric aerosol processes, in particular around the polar vortex. I'll describe a little bit about the Cold SABRE mission, as we call it, the Alaska edition of SABRE, and the methods used in the study. And then just to kind of front load you some of the kind of main take-homes that I'm going to be talking about is basically particles formed in the polar vortex, this descending air in the wintertime, in our case in the North Pole, have a very consistent composition of mostly sulfuric acid, but with a pretty high mass fraction of meteoric metals, so 5 to 10% by mass of metal. And these particles, when they get into the broader stratosphere, they coagulate with background stratospheric aerosol to widely distribute meteoric, and we'll also see spacecraft metals that are also present in this air. And I'm hoping that the new size and composition information I'm presenting should better constrain aerosol formation processes in the vortex. This work is expected to come out in JGRA later this year. It's under review. And please reach out to me or to Greg Schill if you're interested in using these or related data products, because there's a lot currently on the CSL SABRE data page, but we can also do more bespoke products as needed. Okay. So I probably don't have to say too much about this motivating for this audience, but I will say a couple words. So stratospheric aerosol is important because it reflects solar radiation, having overall a cooling effect. It also acts as nuclei for polar stratospheric clouds, which are involved in various processes, including chlorine reactions, so resulting in springtime ozone depletions, denitrification, dehydration. But their variability, they can be really variable in concentration. It's mostly controlled by volcanic eruptions, and that's what I want to convey in this figure down here. So this is from the Global Stratospheric Aerosol Watch from the Latmos website. So this is satellite-based information about aerosol optical depth in the stratosphere. So this is a time series over several decades across latitude from south to north. And you can see that there's the variability in the optical depth goes over orders of magnitude. So there's this big red swath here around 1992 and years after, from the Mount Pinatubo eruption, where you have an aerosol optical depth in the stratosphere around 0.1, which is very high, versus these more quiescent periods in the years that followed, where it can be a couple, almost 2 orders of magnitude lower. And so that, of course, affects the impacts of the aerosol, how much there is. And just to give kind of a taste of how much this variability affects something we'd care about, for example, this study looked at the troposphere temperature. So changes in troposphere temperature as a result of changes in aerosol optical depth. And so at the far right corner of here, you're seeing the sort of Pinatubo case, these downward pointing red triangles where you have increases in optical depth of like 0.1, and this is associated with a cooling of around 0.5 degrees C. So, quite substantial. And one of the reasons that's motivating this work is that there's this idea recently of taking advantage of this feature of stratospheric reflective aerosol and intentionally injecting, anthropogenically perturbing, increasing the stratospheric aerosol to mitigate warming from greenhouse gases, where you'd be, putting in amounts like, Pinatubo scale amounts to try to cool the climate. So we want to understand the processes that are operating in the stratosphere, as a sort of baseline, with sort of a baseline knowledge as these perturbations occur, for example, from this idea of SAI, stratospheric aerosol injection, or perturbations that we are undergoing right now. I'll say a few words about, we're increasing the amount of spacecraft, and that increases the amount of spacecraft reentry events, which increases the amount of that material that gets into the atmosphere. So as we make these sort of perturbations, we want to get ahead of what changes are going to result. So this is from this nice review paper, the Kremser et al. Of the stratospheric aerosol, and it's showing some of the broad processes. You have critically reduced sulfur gases like carbonyl sulfide, OCS, which reaches the stratosphere through deep convection and stratospheric exchange, and you have formation processes of aerosol up above the tropopause, and nucleation and growth of new particles from sulfuric acid. And what we're going to be focusing on here is sort of the far end, where you see these big arrows going over transport. The Brewer-Dobson circulation is broadly bringing air towards the poles at these high altitudes. And what we're going to look at there is, they highlight here wintertime nucleation of new particles. And also, this is where the inputs of meteoric dust actually are going to have the biggest impact. That's where the meteors are striking all over the Earth, but the mesospheric circulation is such that they're brought to the poles, these residual meteor bits, and are expected to go down in the polar vortex. And I'll say a little bit. I thought I'd put this slide in just because, as atmospheric scientists, maybe we don't think about meteors that much. But this is a paper that's sort of trying to get at how much meteoric material comes into the Earth and where does it come from. So this is this total mass influx on the y-axis. You don't need to understand all the details here, but some of the important points to take home are, if we're looking at the top axis here is the radius of the particles. So you can see most of the mass that's coming in is in relatively small meteors, right? They're like sub 100 microns. They're not like what you think of as the big meteor that comes in and makes a big streak across the sky. And the important thing for us is, if we're interested in the amount of the material that might go on to form particles that are present in the stratospheric aerosol, it's going to be the stuff that ablates. So that's what they're trying to show. These different, the open is unmelted material, and then there's two different hash patterns for leaving behind spherules or ablated material. And it's this sort of upward right hatched ablated material that can potentially recondense to form meteoric smoke, which can go on to become a part of the stratospheric aerosol. So I pointed out here, stratospheric aerosol sizes are below here. So these are 10 microns, they're like below 3 microns. So it's not that these meteor particles are becoming stratospheric particles. They're ablating, giving off ions and elements of things, including metals, that can recondense and become particles. Okay, so what do we know currently about meteoric materials in aerosol? So From direct observations, we know that there's actually a large number fraction. If you're from a couple studies flying in and near the polar vortex, there's a large number fraction of particles that when you heat them, they retain a residual core up in this old air, which has been taken as evidence of residual meteoric material. So if you just had pure sulfuric acid particles, they'd evaporate and you would have nothing more to detect. And in other parts of the stratosphere, we've observed meteoric metals in aerosol, so away from the polar vortex, like in the Sitzo et al. Paper, Schneider et al. It's around 50% of the stratospheric aerosol particles contain little bits of meteoric material. So what's the relationship there between this source and the sort of background aerosol? And I'll point out that spacecraft metals, this is just a recent study from our group leader, Dan Murphy, based on some of the observations that I'm going to be talking about today, found that around 10% of sulfuric acid particles in the stratosphere contain materials from spacecraft. So we see sort of exotic metals that aren't present in the meteoric background. And I'll talk briefly about that. Why we care about these materials? Some meteoric components may actually be present as solid inclusions, and in that way may present a surface for ice nucleation to occur on. We don't know if that's an important process. And we also know that in general, metals can catalyze chemical reactions. So especially with the, adding spacecraft material in with sort of more exotic metals, present the possibility that we're going to be doing new chemistry, but very little is known about that, if that's an important change or right now it's purely speculative. And I wanted to show this. This is a modeling study from Bardeen et al., showing basically, what the expectation is for, saying that we expect that the meteoric material is coming down to the polar vortex, and that's what's shown if you look at the top plot here, this is a January case. This is a really high, from my perspective, really high altitude, so from 30 kilometers up to about 100 kilometers. You can see in the winter pole in January, you have this polar vortex bringing down this meteoric material. And by contrast, in the southern hemisphere, that's what's shown in this plot in July. And in southern hemisphere winter, you get the polar vortex, bringing this mesospheric stuff where the ablation of these meteors is occurring, bringing it down into the stratosphere, where it can be incorporated into stratospheric aerosol. Oh, and as mentioned, please, don't hesitate to stop me if anything, if you have a question or comment. Okay, so so let's get down to the project that we worked on a couple of years ago. So this is the SABRE mission, Stratospheric Aerosol Processes Budget and Radiative Effects. This is a NOAA-led effort. And this is the first major deployment mission of this project in 2023. We call it Cold SABRE because it took place out of Eielson Air Force Base near Fairbanks, Alaska, and it was very cold. So we were flying on the WB-57 from the Air Force Base in February, March 2023. Most of the data I'll show are from the PALMS-NG single particle mass spectrometer. I'll talk a little bit more about that in a minute. We calibrated this for organic and iron mass fraction so we could quantify those parts of the particle mass. We also have aerosol size distribution from the AMPS package that has spanned quite a wide range, including the PALMS range. And we have, among other things, trace gases like N2O, SF6, and carbonyl sulfide that help us constrain where air is coming from, and critically, how vortex-like the air is. And so this plot right here is the flight tracks colored by the N2O mixing ratio in parts per billion. And this is basically one of our best tracers for how much of the air that we're sampling is really old air that's associated with the polar vortex, because this air of, say, 350 or so parts per billion, that's kind of background tropospheric values. But as air gets really high, the N2O photolyzes away, and you have in the vortex just really low N2O concentrations. And that's kind of the air that we're targeting on this mission. Okay. And just to say, the plot on the right is just to show kind of the flight altitudes that we're looking at here. So, up as high as around 19 or 20 kilometers, but mostly say like 16, 17, 18 kilometers. Okay, here's just a picture of the WB taken off from Eielson Air Force Base. Max Dolner took this nice shot. The mountains in the background. The PALMS particle instrument is right there in the nose, in the very front of the instrument. Okay, so before I get into the composition of the particles, let's take a look at the aerosol size distributions. So this is a figure from Ming Liu's paper, which is currently in review, where they're looking at basically how the dynamics of the size distribution of the particles. And one of the main take-homes from this mission was that there's this really distinct small particle mode present in the vortex. And so that I'll describe this here a little bit. So here the vertical axis is N2O, and you can think of the top end of that as most vortex-like and generally higher and older air. Compared to the bottom of the plot, this is close to the tropopause. All these data are above the tropopause, but at the very bottom of it, you're basically at the tropopause. And what you can see is up here at the top of this plot, there's this high concentration of particles of around 60 nanometers or so, or that's the mode diameter in number space of the particle size distribution. And this is a new observation. We really didn't have a way to look at this before. What's pointed out here on the plot are it says POPs in Wyoming, and these are other balloon-based size distribution sort of measurement approaches that's showing sort of their lower size cut for their particle sizing. So we really didn't have a way of looking at this before, and so this is a new observation that you have this high number of small particles up here. And so we'll talk a little bit about what they are in a moment. Before we go, I just want to point out, just for a little bit of context, now this second plot is a diameter space. So this was a number size distribution on the left. On the right, this is a volume, or you could think of it as a mass size distribution of the aerosol. And you can see what pops out in the mass is all of a sudden there's this really strong mode around 600 nanometers, and we're attributing this to the Hunga Tonga eruption. This basically appeared, this aerosol from this southern hemisphere underwater volcano ultimately made it up to the northern hemisphere, and by 2023 in March, when we were sampling it, there was aerosol present from that, and we think that's what that larger mode is from. Okay, so now I want to look at composition of the particles, and our tool for that is PALMS NG. So this is called the particle analysis by laser mass spectrometry. We call it the next generation instrument, and this is just a couple of years old. The original PALMS, we affectionately called old PALMS, has flown for around 20 years. And this new design is basically, the main innovation is that there are now two mass spectrometers on it. So for every particle, we can look at the positive and the negative ions that result when you ablate them to see their composition. And so this paper's from Justin Jacquois, paper describing PALMS, and I'll point out that these, to get to this innovation of having the two mass specs, Dan Murphy invented this so-called S-TOF, this S-shaped TOF, which can do is quite a compact version. Before there was this long reflectron on the old PALMS instrument, but now we have this really compact, efficient, so-called S-TOF mass spectrometer, and a pair of those. And so the way this works, just to get it in your mind, it's a single particle instrument. So we look at the composition of individual particles. Particle goes in through the inlet here. There's an aerosol focusing inlet. Takes a particle up into this first region. This is where it first interacts with a laser beam. We call this the timing beam. Particle continues on its path into the center here of the ionization region, and there it interacts with a second continuous laser beam. The triggering laser beam, the time it takes to get between the two tells you how big the particle is, its aerodynamic diameter. And then that second laser beam also triggers a laser pulse that ablates and ionizes the particle. As a blast, it basically explodes it. And then the resulting ions are electrostatically forced to the two mass specs, and you get a spectrum of each individual particle. This works down. We're limited by our ability to optically detect the particles, and so we can get down to about sizes, in this study, of around 120 nanometers in diameter. Okay, so here's a typical mass spectrum that we would get, or a pair of mass spectra that we would get from an individual particle sampled this way. This is what I'd call a typical meteoric sulfuric particle sampled in vortex air. So It's mostly made of sulfuric acid, but there's a lot of peaks there, a lot of metal peaks. So that's indicative of the meteoric material that's present here. So you have 56 AMU, you have iron, magnesium, sodium, aluminum, calcium, potassium. There's also some carbon peaks. You see a sulfur peak, but most of the sulfur signal you see in the negative ion, where all these peaks really are from sulfate or sulfuric acid. Okay, so one of the real strengths of PALMS is its ability to classify particles into different types that have different, basically, origins or like formation histories. And that was probably some of the main work that went into what I'm going to present today is sort of distinguishing these types so that we can use them to say things about the dynamics of the aerosol population. And so I'll say there are basically 4 main types of particle that we observed in this study that are worth distinguishing for the purpose of this talk. And I've shown them here. I gave them sort of cartoons, that you're going to see these cartoons a couple more times to try to, because there's a lot of, it's kind of doesn't become too much of a word soup here, but basically showing the essential composition and size of these particles. So we have, maybe I'll start with this kind of very familiar, sulfuric acid. You can think of this as sort of like background stratospheric aerosol. It's almost entirely sulfuric acid. That's what's in blue here. And a little bit of organic, so like a percent or fraction of percent of organic material. And then you can compare that with, say, like a sulfate organic particle. These tend to be smaller. These are tropospheric-like particles with large organic contents. Now let's talk about the two flavors of meteoric particle that we observed. So I'm calling this one neat meteoric sulfuric particles, neat to convey sort of a simple composition. They contain very little organic material, and these are the ones that are really typical of the vortex. They're part of that group of small particles that we see up in the oldest air. They're mostly sulfuric acid, but a relatively high fraction of metals. And then we also, in the background atmosphere, the background stratosphere, we see what I'm calling aged meteoric sulfuric particles. And these are more variable in composition, but can have a little bit of organic. That's what I'm showing here in the green. I don't mean to convey that these are somehow phase separated, these different components of the aerosol. This was just a convenient way to show the different relative amounts by mass of these components. Okay, so that's the cartoon vision of it. What actually is the composition of these particles on a size-dependent basis, and that's what we're looking at here in these 2 plots. So the lower left plot is looking at the organic mass fraction versus diameter for these different particle types. You can see there's this very different from all the others is the sulfate organic particles. These basically come from the troposphere. They're not really made in the stratosphere. All the other types are mostly sulfuric acids. Their organic mass fractions are quite low. But you can see these sulfuric acid particles. They can have a couple % of organics at the small sizes, but as they grow to larger sizes by addition of sulfuric acid, they're really mostly sulfuric acid. And these, in the black trace here, these neat meteoric particles, they have the lowest organic content of any particles really that we measure, I would say. So we can detect some organics in them at small sizes, but out here above, say, 200 nanometers or so, they're just really organic poor, coming from this vortex region where there's the expectation that the air has seen a lot of UV radiation, and a lot of the organics that might have been present have been photolyzed away. And the plot on the right is the metal mass fraction in the 2 types that contain meteoric metals. So the black is these neat meteoric particles from the vortex. So I was saying before, they're only order 5 to 10% by mass metals, and that's across sizes. So it's not very size dependent. That's basically this really consistent composition that they have compared to the aged meteoric that are in the background stratosphere. They can have this wide range. And the reason for this is that, I'm going to make a few more arguments about this, is that basically these aged meteoric particles that account for something like 50% of the particles in the stratosphere are a result of these small neat meteoric particles from the vortex coagulating with large sulfuric acid particles that are present throughout the stratosphere to form this sort of mixed aerosol. Okay, so peeking into the vortex. So if we try to look at the very oldest air, most vortex-like air that we encountered on this mission. So to do that, we look at the lowest N2O values. So I'm going to show some data from N2O values of 100 to 130 ppb. So it's really highly vortex-influenced air. And what I'm showing is basically we have size distributions of these different particle types. We take the total size distribution from the AMP package of aerosol. That's what's shown in this black trace on the left here. And then we know the fraction at any given size of these different particle types that I discussed. And we basically can map that onto the aerosol size distribution to get size distributions of individual kinds of particle. And so that's what's shown here in the colored traces on this left plot. This is number size distributions of neat meteoric particles, so they're in red now, and then aged meteoric in green and sulfuric acid in blue. And what jumps out at you is that, and so I shall point out, we can only measure down to, this is around 150 nanometers, so we can't directly observe particles with palms that are smaller than around that size. But what jumps out to you is in this old air, the number concentration is mostly these neat meteoric particles that are really low organic and have a high metal mass fraction. And in fact, we would, of course, really like to know directly what's in this this number mode at 60. This is about 60 nanometers, and there's a smaller mode, or a larger diameter mode, but lower concentration mode at about 120 nanometers. And we'd really like to know, what's in this one too. And I'd argue that we have a little bit of information about that actually, because we're probably, if you consider these two modes are each well fit by a log normal function, and so that's what's shown in these gray dashed lines. And so we fit the two modes to a log normal function, and what you'll see is that down here at this, at sort of the edge of where we can measure with palms, the colored points, we're collecting a small number of particles from this, like the tail end of this small mode. And that's what I'm trying to show on the plot on the right here. We're looking at the fraction of particles. Take a look at the dashed line first. So this is the fraction of particles that we expect is from this sort of smaller diameter mode at any given size. So, if you're measuring out at 60 nanometers, they're all from here. But if you're measuring at sort of the bottom of our range at around 150 nanometers, there's about close to 10% of the particles are probably from this smaller diameter mode. So we're collecting some of them, but not so many. So then it's relevant to look at the fraction. How does the fraction of these different particle types we measure change with diameter? And as you get to smaller and smaller diameters, these neat meteoric particles from the vortex increase in their fraction, the aged go down, and the sulfuric also go down. And that's, it's inferential evidence that probably the particles in this small mode are also these neat meteoric particles. The alternative composition for them would really just be pure sulfuric acid particles. Sulfuric acid particles that nucleated without a meteoric smoke core and have essentially nothing else but sulfuric acid. So we can't directly make that measurement. We have this inferential measurement. I'll point out, you might wonder why, what is the source of this kind of bimodal structure in these particles? And there's one study, unfortunately it's still just a preprint. It's based on an AGU presentation from a few years back by Graham Mann. They did some modeling about this, and essentially their result was they expect to see in air like this a purely condensationally grown mode at around 60 nanometers. So that's just the meteoric core with sulfuric acid growing onto it, and a larger mode in around this size range that results from coagulation of those condensationally grown particles. So that's a likely explanation that would be consistent with our results for the structure there. And to add a little bit to the sort of constraining the processes that are going on there. So one thing that we discovered about these particles, these neat meteoric particles, is that the larger they are, the more likely they are to contain spacecraft materials in them. And so that's what's shown on this plot. So the y-axis is the fraction of these neat meteoric particles, these vortex originating particles that contain above some certain threshold of some anthropogenic metals, so from spacecraft. I've included niobium, silver, aluminum, copper. Niobium is part of rocket cones. The other three are mostly from satellites. And of course, aluminum is also present in high abundance in meteors, but I'm looking at a threshold above what's the meteoric background. So you can see as you go to larger diameters, you're more likely to encounter these metals. And this is not like a detection limit sort of thing. We're actually quite sensitive across all these sizes to these metals. When I first thought, oh, that's exciting, there's this causal relationship, like, oh, spacecraft's coming in and it's messing up the size distribution somehow. There's gonna be a science paper or something. But we think the more likely explanation is probably that because these particles are probably growing in the vortex by coagulating, essentially they get bigger by having more coagulation events. If you have more coagulation events, you're more likely to have an event where you've encountered a spacecraft dust particle, basically. So there's sort of a statistical reason to expect that larger ones would be more likely to have these exotic particles or exotic spacecraft stuff because they've just encountered more particles during their lifetime. Okay, so I showed you a moment ago this size distribution of particle types in this really old air, low N2O air, and now we're going to expand that to basically the whole sample domain near the polar vortex. So instead of just looking at this sliver from 100 to 130 nanometers, let's look at the whole range of N2O values at the number size distribution of these different particle types. And so that's what these plots are. So if we look at the topmost plot, this is specifically for these neat meteoric sulfuric particles that I contend originate in the vortex. And that's essentially what you see here is that you have, there's the sizes on the x-axis, but the highest concentrations are in the oldest air, the low N2O air, and they're also at the maximum at these small sizes. So the smallest this is Palm's data, so we have some lower limit here of around 150 nanometers. And so that's, and you can see in the youngest air, so closer to the tropopause, down at the bottom of this plot at 350, you almost don't see these particles. They don't make it down that low in the stratosphere. I contend, coagulate away by that time. And so compare that with what I'm calling the background meteoric containing particles, these aged meteoric sulfuric particles. They span the size space. You see them up to over a micron, and the N2O space. So they're present throughout the whole stratosphere. There's not really much evidence that there's a higher number of them near the vortex. They're not coming directly from the vortex. They're a result of processing of vortex particles in the atmosphere. But you will notice they look a lot like the sulfuric acid distribution. So this is the background stratospheric aerosol. Mostly not formed near the polar vortex. It has a very similar distribution to the aged meteoric sulfuric. Again, because basically I think on the second plot, these aged meteoric sulfurics are basically, you have a sulfuric acid distribution in the background atmosphere. All you have to do is add like a little 60 nanometer or 100 nanometer meteoric particle, and then you have a distribution that looks like this. It doesn't change the size of these particles much at all, but it just gives them meteoric metal. And that's, I think, the way that you're distributing this stuff from the vortex, meteoric and spacecraft stuff, over the broader stratosphere. And I'll just say the bottommost one, the sulfate organic particles, there's my guide to the composition of the particles on the right there. These are the ones that contain a bunch of organics. These are from the troposphere. You can see that, obviously they have high concentrations at the tropopause. And by the time you get to this old air and low N2O air, you basically don't see particles like that. They're really tropospheric sourced, and they go away in the stratosphere either by coagulating with bigger sulfuric particles or growing up by condensational growth of sulfuric acid. And if we looked at, say, biomass burning particles from the troposphere, you'd see a really similar picture to what's there for the sulfate organic particles. If you want to look, you think a little bit more about volume space, you want to think about the mass of the particles. I think about number a lot because I think it's useful for particle formation, but you think about volume or mass of these particles. That's what's now here on the right column. And you can see that those neat meteoric sulfuric particles from the vortex are not really a lot of mass compared to the other particle types. And what you can also see is when you look in volume space, you can see this Hunga-Tunga mode a little bit better, the 600 nanometer mode. Like if you look at the sulfuric acid particles, it pops out there. And also in the aged meteoric sulfuric particles, you can see it there. This is sort of another piece of evidence that you get these aged meteoric sulfuric particles by coagulation, because you have this Hunga mode that's swept in through, it's already aerosol phase material, swept in through to the northern hemisphere, and has this strong mode at 600 nanometers. And then to get an aged meteoric sulfuric particle, all you have to do is get one of these little small ones from the vortex to land on, and then you get a distribution that looks like that. Okay, so I've been making this argument that it's really coagulation that's controlling the dynamics of these meteoric particles. So we can look a little bit more quantitatively at the process. So what I'm showing here is coagulation lifetimes of these different particle types I've talked about, sort of bin by N2O, which inherently also is going to bin it in pressure and temperature space, which is necessary for doing the calculations. So again, we have this N2O vertical axis where you have more vortex-like air on the top and more closer to the tropopause-like air on the bottom. And the x-axis now is coagulation lifetime. So how long, like what's the e-folding lifetime of particles of this type to loss by coagulation? So if we start look at the red trace as a starting point. So this is neat meteoric sulfuric self-coagulation. So those low organics particles coming from the vortex, what's their lifetime to coagulating with themselves? In this old air, where there's not that much other stuff up there, it's fairly long. So this is about on the order of about a year. What's their lifetime to coagulating with other stuff? How quickly are they getting lost to other particles that are there? In this old air, it's very slow. It's on the order of about 3 years. That you actually reduce the concentration of the neat meteoric particles by coagulating them with other stuff. But on the flip side of that, when you're talking about these coagulation, these different groups, it's not symmetric. So what if you think about the lifetime of those big sulfuric acid particles, a handful that are around, with respect to coagulating with these neat meteoric particles? That's actually pretty quick, because there's relatively few of these big sulfuric particles, a lot of these little neat meteoric particles, and it doesn't take much to change your number of particles that have interacted with a meteoric particle. So that's on the order of like 3 months. That's what this pale blue trace is. So that's the lifetime that sulfuric acid needs to take up meteoric material. So that's pretty quick. And in terms of like stratospheric dynamics time scale, that's a pretty short lifetime for sort of background stratospheric aerosols to take up this material. So I'd say this is consistent with this idea that this is a viable pathway to get this material into the background stratosphere. And as you can see, things change a great deal as you go down in the troposphere. Like if we look at the lifetime of neat meteoric particles to coagulation with everything else, that's black. As those decrease in number and the concentration of other particles increases in number as you get lower and lower in the stratosphere, this lifetime drops off so that it's on the order of days or a couple of weeks. So those particles that originate in the vortex, they're not going to make it all the way down to the tropopause, which is consistent with what we saw in the size distributions there. By that time, they're coagulated away. Questions? Not yet. Okay. Okay. So then we looked at size distributions, volume and size distributions of these particles across this sort of polar vortex region, and if we integrate those now, we can integrate those size distributions and get actual mass concentrations of stuff that we're interested in. So for example, the meteoric metals. So here again, this is an N2O space, and now I'm plotting it over latitude bins for the whole study, including transit flights from Texas. And just to give you a rough idea, the range of altitudes around 12 to 17 kilometers. And so you can see that this is on the order of a couple tens of nanograms per meter cubed at SDP of material. And, salient point is that there's obviously higher concentrations in this older, higher air, low NTO air, and much lower concentrations, because this is, the source is up here in the old air. Yeah.
Left corner grey because you just didn't look there?
That is correct. So all the gray is out of the sample domain, I guess you could put it, yes. And there aren't a ton of points of comparison for these observations. I think I mentioned Chuck Bardine's paper maybe earlier, and he led a modeling study showing the first 3D modeling study showing where the meteoric dust ought to go, and that's what's shown in this plot here. The sample domain, the model domain they're considering is a little bit higher up. You can see that the lowest point is about 30 kilometers, and our upper point is around 20 kilometers. But you could imagine, and this is also with latitude. So this is in January where the polar vortex is present, and so this is roughly comparable, at least seasonally and spatially, to the upper end of our measurements here. And you could imagine if this plot went down to 20 kilometers, it would probably be kind of orange and yellow over here. And so if we look at the orange and yellow values on their color bar there, that corresponds to around 20 nanograms per meter cubed SDP in our units here. So in the middle of the range here, so quite close, I would say, for a model study that wasn't really intended to match our particular observations. I think we're in the same ballpark for how much stuff is there. And we can also, we also want to see how does this compare to what we know about influxes of meteoric material from space. So this top estimate here is from Carrillo Sanchez et al. Is an estimate of, based on all that the meteoric size-based what's coming into the atmosphere data that I showed like in one of the early slides. How much stuff do they expect from their model to ablate? How much iron do they expect to ablate from these meteors and be available for formation of aerosol? And it's around a ton of iron per day that meets those criteria. And so then we did a couple of very rough, you could essentially back of the envelope calculations that we could do without doing actual 3D model simulations. So the first one, we're saying, what if we look at sort of background mass fractions of this stuff outside the vortex and compare that with sort of the typical average OCS flux of like stratospheric aerosol forming carbonyl sulfide flux, and say that this is sort of like a steady state argument, even though the atmosphere is not in steady state with this stuff. But it's an easy calculation to do, and we get the right order of magnitude, like at 0.8 to 1.7 tons of iron per day. Another way that you could approach it is, well, let's say the stuff that's coming in through the vortex, we know the concentrations of these neat meteoric particles and how much metal's in them. Let's say, that's everything that that amount that's coming in to the stratosphere. Say that's typical of like a broad surface at around the same altitude range that we have a number for. So there's this Lintz et al. Paper where they look at the strength of the overturning circulation. So you have, estimates of the movement of mass of air over different, say, like potential temperature heights, potential temperature surfaces. And so we said, okay, so everything over a 450 potential temperature surface, kind of similar to our measurement, potential temperature is like what we observed near the vortex. And then we get an estimate around like 2.5 tons of iron per day. Maybe a bit of an overestimate, which considering the calculation, probably ought to be a bit of an overestimate. But the point of this is basically that these observations are consistent with the idea that these neat meteoric-sulfuric particles are the main conveyors of meteoric mass out of the mesosphere and into the background stratosphere. It's about the right amount of material that we measure coming down. Okay, so the picture that I kind of want to leave you with here is the conceptual diagram of the processes that I've been talking about, that I think is sort of my view of what's going on overall. So this figure is split up into the mesosphere, stratosphere, and troposphere. And you can see at the top of the plot, you've got meteors and spacecraft coming in, ablating in the mesosphere to form meteoric smoke particles, just mostly metal particles. As those are brought down in the wintertime polar vortex in either the northern or southern hemisphere, eventually they cross into the stratosphere where there's more sulfuric acid, and that condensationally grows these particles, so they become mostly sulfuric acid, and they coagulate as well. And then they form what I'm calling these neat meteoric sulfuric particles. I'm still flexible on the name. If someone has a better name for them, I'm open to that. I'm not sure about fresh because I don't know how old they are, but that was another alternative. And so so these guys I'm saying are coagulating with the background stratospheric aerosol, which tends to be larger. And these background stratospheric sulfuric acid particles are either coming up from the nucleation out of the gas phase, reduced sulfur getting oxidized to H2SO4 and growing new particles, or potentially from particles that cross into the troposphere or into the stratosphere from the troposphere, and then are grown by coagulation or condensational growth by H2SO4. And so these have a quite consistent composition across our, all sizes. They're really low organics, really high metal mass fractions. And whereas these coagulated, aged meteoric sulfuric particles have a variety of compositions because there's a variety of amounts of organic material that you can get here. There's a variety of sizes that they can, of these background particles that they can coagulate, which then, of course, affects the ultimate mass or the mass fraction of the stuff in the particles of the meteors and of the organics. And these, as I said, these aged meteoric sulfuric particles are ubiquitous in the stratosphere, around 50% of the mass. Okay, so I'm going to leave you with that picture. Oh yeah, the next work that I'm doing in this area is we're trying to quantify these spacecraft metal fluxes. So we did some calibrations of some of these kind of exotic spacecraft metals, and we're trying to get those estimates of those fluxes to compare with what's known about satellites. And I just want to say thanks. And again, contact me or Greg if you have questions or if you want to use some of this data for anything. And I'd be happy to take any questions. Thanks.
Questions in the room?
Yeah, Michael, that was very, very, very interesting. Do you think, what's the difference with the stratosphere over the South Pole? It's colder, so you have more PSEs, probably more condensation and kind of stuff, and probably less organic stuff coming through than the Northern Hemisphere. Would that look like the same or similar?
Interesting question. I have not thought that much about the Southern Hemisphere. I mean, I would expect a very similar picture for these neat meteoric sulfuric particles in that they don't basically have that much organics, but as far as the other, whether the backgrounds, I guess the question is really whether the background stratospheric sulfuric particles have much of a different composition. I'd say that would be the main control. I would say, I think that's a plausible hypothesis that there'd be less organics, but other than that, I don't have a strong sense for how they'd be different. Yeah. Interesting question.
Any other questions in the room? Well, Holger stole mine, but I have another one for you. Obviously, you're limited by the observations that you have, but do you have any feeling for the efficiency of any of these different compositions in serving as ice nucleating particles?
The the key, I guess, is you expect that you need like a solid inclusion. Most of these metals are thought to be present in a dissolved state. At least, these particles in the stratosphere are almost entirely sulfuric acid, and most of the metals in them are dissolved, like the iron, the aluminum. We expect mostly to be dissolved, especially the iron. The aluminum maybe not, but something like silicon has a potential to be present as a solid inclusion. So there's like a handful of things that may be that way, and really we actually don't know that well which things will be solid inclusions.
That's fair, but thanks for taking a guess.
Can I add to that question? If they're all included in particles, would they contribute much to gas phase chemistry?
Only to heterogeneous chemistry. Yeah. All the, so the only stuff that recondenses from the meteors and the spacecraft stuff is, like low volatility stuff. So I mean, there's meteors also have carbon and stuff in them, and maybe there's complex organics in the original spacecrafts, but those are probably CO2 turned into CO2 in the mesosphere. So.
Okay. We have a question online from Simone. Do material from spacecraft come down everywhere or mostly over the poles?
We think it's mostly over the poles. So I mean, dynamically, that's the expectation that the mesosphere, all these ablations occurring in the mesosphere, the expectation is that air all gets dumped into the polar vortex in the winter hemisphere. That's what the model simulations show, and I'd say our observations are consistent with that because we have basically enough metal coming in through the vortex to explain what we expect the sort of total Earth flux to be consistent with. So yeah, that should probably mostly all coming in the poles.
Great. Any other pressing questions from the room? All right. Well, I don't see any more questions online, but you've definitely given us a lot to think about. I know I have some more questions I'll probably follow up with later. But let's thank Michael one more time.
Thank you.